Hi, this is Professor John Lamb, and welcome to Manipulations in Mathematics. Today we are going to talk about two-color counters. Two-color counters are counters that are very helpful in the younger grades to help with understanding and become rational counters. But they're also helpful in the upper grades to deal with positive and negative numbers. So these two-color counters have two sides. They have a red side and they have a yellow side. And one thing that you can do with them early on with your younger students is you can work on, say, a benchmark number of 10. So you have 10 two-color counters in a row or in two rows like this, and you start writing down all the ways that you can make 10. Well, first starting off with 0 red and 10 yellow. So 0 red plus 10 yellow equals 10 counters. Then you can flip them over and say 1 red plus 9 yellow equals 10 counters. Then you can have 2 red counters plus 8 yellow counters equals 10 counters. And you can do this all the way up until you get 10 red and 0 yellow, which is going to be the last way that you can add to 10. One thing that this builds in early childhood or early childhood mathematics understanding is the fact that I can take two, if we're putting red first, I have 8 red and 2 yellow equal 10. But then we can also do the reverse and say 2 red plus 8 yellow equals 10. And so it's an early understanding of the commutative property to where you can say 2 plus 8 equals 10, or you can say 8 plus 2 equals 10. One thing when I talk about rational counting with your younger children, the rational counting is this idea that you have 4 elements. You have 4 elements that define or help you understand if a student is just a rote counter or is a rational counter. And when I say rational counter, the first thing that we need to make sure the kids can do is count in a sequence. We want to make sure that they can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and so forth and so on. One important aspect of that counting in a sequence is that some students, in early age, you're going to start counting to 10 and we use our fingers, or then we can move on and count to 20 and count by 10s to 100 or count by 2s to 100 and various things that you want to practice, but sequence is important. And they need to know that there are only specific names that we give them, and there are no 11 teens in the world, so we don't use the word or the number 11. So we have a correct sequence. And then we have this understanding that each counter or each object is counted one and only one time. So there's a one-to-one correlation between the number of objects. Each object is assigned a number. So 1, 2, 3, 4, 5, and so forth and so on. Well, one thing that early counters, rote counters make a mistake in doing is they'll count 1, 2, 3, 4, 5, 6, 7, 8. So they'll give multiple numbers to the same element in the set. So we want to make sure our students do not or practice only assigning one number per object. So there's a one-to-one correspondence. Then we go into, it doesn't matter how you count the counters, you'll still get the same number. So if I count them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I can still get 10 by starting from the other side and going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. One other element of this counting, and it doesn't matter what order that you count, is this idea of conservation of a number. In other words, if I add 5 this way, then I can also add 5 this way, and I can also add 5 this way. Oftentimes, early learners think that this way of arranging your number equals more than this way of arranging because it is longer. So when you illustrate it 5 next to 5, some kids don't have a kind of a conservation or understanding that this length of 5 is not more because it's longer, it's the same because they have the same number of elements. So to review, when a counter is a rational counter, you count in a correct sequence. Each element gets one-to-one correspondence, or just gets one number. They have an understanding that it doesn't matter what way you add, the order doesn't matter. There's that idea of conservation of number. And then the last thing that makes a rational counter is the last number counted is the number of elements. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is the last number that is counted. So therefore there are 10 objects in place. So this is an early introduction to two-color counters. Another way, just real briefly, that you can do this understanding of making tens is you can have students put their two-color counters in a cup such as this, spill them out, and then divide them up into the two different colors and record their answer. So here would be 6 red plus 4 yellow equal 10. Of course, you can do this with other elements. I'm going to say now there's 13 in our cup. So we want to find all the ways to add up to 13. So we shuffle the cup up and then spread it out, make our groups, and then do our counting. So in this case we have 6 red and we have 7 yellow. So 6 plus 7 equals 13. And you do this with various things. You want the kids to then get their pencil, record the answer, and then keep practicing that. You can do it in pairs, do it in groups, but you want them to do some addition, early understanding of addition with your two-color counters.